Okay, so now we know the conditions wherein we will have a integral or energy that for the probability of this transition to be zero or not. And basically the key comes down to it will only be non-zero if psi I times psi j has the same symmetry as H, as we explained previously. So what is the Hamiltonian H? For different processes is different things. And hopefully those of you who are taking physical chemistry are learning this or have already learned this. So for spectroscopy, and specifically talking about vibrational spectroscopy, we have something called mu, and that's what we call the Hamiltonian when we're talking about vibrational spectroscopy. This is called the transition moment operator. And the intensity of a spectroscopic transition of a peak is directly proportional to that top integral, that numerator that we went over. But now we have actually formally we've put in psi initial, psi final, so that's like a ground state and excited state, and then mu, and then d tau. Tau again is all symmetry space, right? So that's very frequently very high multidimensional space if it's a very high point group with a large order. So we can now say, just by analogy to the previous slide, that only if psi initial times psi final, the product of that is the same symmetry or contains the same symmetry as the transition moment operator, mu, only then will the intensity of the peak be non-zero. And for what is the transition moment operator? For infrared spectroscopy, if you're talking about absorption of infrared light for that process, the transition moment operator is x, y, or z. So it's an x vector, a y vector, or z vector. And it's practically for most experiments, it's all three of these vectors. But strictly speaking, it's x polarized light for the x vector, y polarized light for the y vector, z polarized light as a z vector. How do you define x, y, and z? Well, z is defined as your principal rotation axis, right? Like we talked about all this time. And again, this is the same sort of integrals, but now I've plugged in x, y, and z to get the intensity with these different polarizations of light. Again, for most experiments, you're not polarizing light, you're just shining normal light at it. And so it's the sum of all these integrals, right? But these integrals are across all symmetry space, d tau. So we can write it like this, just generically with mu, the transition moment operator, and the intensity, not caring about the different polarizations of light. Psi initial is the ground state wave function, okay? And so when you're talking about vibrations, the ground state is when nothing's vibrating. So with respect to those vibrations, it's totally symmetric. You don't have one thing vibrating out here to give you something anti-symmetric. It's symmetric with respect to vibrations. So the ground state is always going to be the totally symmetric representation in whatever character table you're using. It's going to be A1G or A1. It's going to be ones across the board in that irreducible representation, that first row in all of your character tables. So we know that, right, the totally symmetric representation times anything is just itself. If you say, look at any product table and you look at A1G times, let's say, E, that's going to be equal to E. If you have A1G times T2, that's going to be equal to T2. If you have A1 in a different point group, let's say with the totally symmetric representation, A1 times A1, that's A1. So A1 times anything is itself. Why? Because you're timesing everything, all the components of the vector by 1, because the totally symmetric representation has 1. So essentially, psi initial drops out of this equation, okay? And now this really gets simple. We've gone from something that looks pretty gnarly, the Schrodinger equation, and we're getting it down, paring it down to something pretty simple. And this is, it'll get even simpler. And this is the beauty of group theory. Group theory, as I mentioned on the first day of class to you guys, group theory is so powerful because it allows you to take something that's very complicated, that i.e. quantum mechanics, the math of quantum mechanics is very complicated and hard and difficult to intuit. Basically, you need a computer in most cases, right? Group theory allows you to do things on the fly with pen and pencil or in your head, which is pretty cool. So that's really the beauty of group theory. So we're left with this integral where now we just have two terms, the transition moment operator and psi final. And psi final, what is that? That's the excited vibrational state. We're going to call it nu equals 1. Nu equals 0 is the vibration state. You might remember this comes from the harmonic oscillator approximation. Again, some PChem stuff here, but we draw something like this, right? And we'd say nu equals 0 is that first line here, nu equals 1. And so most of the time, what we're talking about when we're talking about a peak or absorption process in absorption spectroscopy, we're talking about a transition going from 0 to 1 right there, something like that, okay? Remember that there's 0 point energy, and so the bottom of your harmonic oscillator well isn't at the same level as nu equals 0, your ground state. There's some 0 point energy that puts you up, but that's not super important. Anyway, just reminding you about the harmonic oscillator. We'll go back to this picture a little bit later in the course as well. So your selection rule now is very simple. If you're just looking at the symmetry of mu, your transition moment operator, which is x, y, or z, depending upon the polarization of light, and psi final, which is the symmetry of your excited vibrational state that you're trying to get to. And because of all the integral rules and the product table rules that we've gone over, we can say now our selection rule, the intensity, i.e. the intensity of a peak, is only going to be non-zero if the product of mu and psi final contains a totally symmetric representation, right? Because only then will the integral be non-zero, because it can't have any odd functions. And that only happens according to our product table rules when psi final and mu are of the same symmetry. So it boils down to just looking, hey, is my excited state symmetry the same as mu? Okay? And so let's keep this in the back of our head, and now we're going to talk about normal modes and eventually come back to this concept and be able to tie it all together to predicting IR spectra.